Hello everyone. Welcome to the second webinar in our CryoSCOPE webinar series. Today, the presentation will be given by Mikko Strahlendorf, who will be presenting some of his work on seasonal streamflow forecasting in Iceland using different machine learning approaches. A bit of background about Mikko. Mikko works at the Finnish Meteorological Institute, where his work centers around the European Organization of Research, Infrastructure, and Environmental Information Systems through multiple programs such as the Copernicus Earth Observation Program and the Integrated Carbon Observing System, the ICOS project. Mikko has gathered experience in European Union policy support development. Currently, he's very active in climate service development in EU-funded projects like CryoSCOPE. Mikko will be presenting his work on streamflow forecasting for Iceland. The format of this presentation would be that Mikko starts presenting, and if you have questions, you can either put them in comment or you can raise your hand, and feel free to interrupt Mikko during the presentation, or if you prefer asking questions at the end, that's also fine. So either raise your hand or put your question in chat. So without further ado, I will now hand over the mic to Mikko.
Thank you very much, Harsh, and really good to be here. And I do have to kind of remind everybody that most of this work, as in coding and producing products and material in this presentation, is actually from Golda Prakasam, so my colleague in our group. So I am more like her mentor and guiding person, and then she was the workforce behind this, so I think a lot of credit belongs to Golda. She unfortunately had to move to other tasks that our group has to do, so that's why she's not available to present herself. Let's go forward. So Iceland and streamflow prediction is what we are looking at, and it is just for a background to good understand that in Iceland the energy system is very much kind of renewables based, and most of that renewable actually is hydro, especially the one that is behind the like electrical power generation, and therefore and it is structurally so that a very large part of it is either on the south east side, on the southern side, or on the eastern side. There are like two places where these hydropower plants are located on the very many vast and big even rivers that Iceland has. So really 100% renewables and really dependent in a way on this source that is not a constant all the time. So understanding and being able to forecast that also longer than just a few days ahead is a key point why we are interacting here, and it has a very direct link to economics of this country. But there is changes at the moment. So the glacier melt that has been observed in '95 is not as steady as kind of like before, and especially that comes probably from there being less seasonal snow, because climate has also changed in Iceland already. So we are not anymore in a normal from past decades, but we are in a kind of sliding situation. And that makes it more challenging to time when water is available. So hydropower being to control when to let it flow out and when to leave room for kind of new water to come in is pretty crucial. I think hydropower generation is good to understand. You want always to avoid having to just make it flow through. You always want to be the one to say when does the power production happen, and that means that you have to have some room in your reservoir and still be able to kind of like operate enough power generation. But this leads very much to the fact that the challenge here is that longer term looking forward is useful, and that's why it fits well into this scheme that really our group has been very active in many projects, that we are not just looking at the weather forecast time frames of like a week or two, but we are looking into this seasonal forecast time frame, which is 215 days ahead in these forecast products. That means it's almost 7 months that we are looking forward, and that's a time frame when like the forecast material is always in samples. You are not having as kind of high resolution and kind of, it is more coarse, large scale modeling that you get. Therefore, we need this kind of an approach where we actually do a bias adjustment, which also downscales these seasonal forecasts into material. But here, as the example where we want to kind of give an inflow forecast or kind of a probability distribution of what the inflows could be in the coming months or hundreds of days, that is really a scheme where we try with ERA5, or well, we do make a machine learning model. We use extreme gradient boosting based on these longer observed time series of our target. But what is the kind of features and predictors that help us to explain it is that mostly it's ERA5 and ERA5 land. So for the surface parameters, ERA5 land. And in some cases, when also the upper atmosphere material is important, we also use ERA5 pressure level data sets. In this case, it's mostly those ERA5 land material that helps to do it. We also use a lot of the Earth observation kind of static or kind of higher resolution analysis of, for example, orography or vegetation, things like this that also explain that's kind of predictors to this kind of target. And obviously, it's very important also to include, and we pretty much operate only on the ECMWF IFS, so the integrated forecasting system model, that you understand how that model is parameterized. So, for example, soil types and things like these are all put into a certain resolution in the ERA5s, but then you have that information also on the higher scale, so you can also through that get more detail. But this is really making a machine learning exercise. Then we get a model that can downscale and predict a certain specific parameter. And in this case, it's really the inflow to hydropower plants. So we do kind of stream flow forecasting for all the river sections. And how we generally get successful is that we use really extreme gradient boosting. It usually is winning all kinds of competitions, but like the whole thing is about getting a good target information. So a longer time series, usually at least 5 years, shouldn't have missing data, has to be less than 5%. But in optimal cases, for example, in this one, you get over 20 years of data, because that includes then also some extreme events in all directions. So a lot of river flow, or almost like no river flow in this case is the extreme. So, and you wouldn't have any missing values in the time series. That's the optimal thing, and we pretty much got it here. And then, yeah, in some cases you can fix these time series, but mostly that's very crucial for a good machine learning model, is always to have a good target and enough data of that target. In tuning, we are using both OpTuna, a tool that makes it very convenient to there are many hyperparameters in extreme gradient boosting model, for example, which you don't want to understand too much about, because it's easy to just go through 100 tests of this training material that you have and give wide ranges for these hyperparameters. And there's a way that it optimally finds hyperparameters that work best. We also do k-folding for the splitting the training and validation data sets into different parts, so we optimize that split. Yeah, but that's kind of how we do the initial model, where everything is in. So we try not to kind of like choose already from the ERA 5 or ERA 5 land parameters, for example, anything, we just chuck in everything, because that is kind of like also giving us the opportunity to teach the model physics that or the physics of the whole problem into this machine learning model. We then use Shapely. Game Fairly has this tool for explaining the AI. And with these SHAP results, we then understand which variables or features, predictors, are impactful. And those most impactful ones we keep, but some who have very little impact or even like extreme gradient boosting can in principle also kind of leave out some features because they have no meaning or they're very weak explainers. So these might drop off by themselves, but mostly everything gets somehow in, but you can still kick out a lot of the weaker features from the Finnish like final inference production system, which without sacrificing much quality. And that part is then in a way feature engineering where you tune those predictors. But one of the feature engineering that we usually already now beforehand put in, that when you do have a climatology of the target, that is many times straightforward, especially if you have Earth observation like satellite data sets or even from some kind of other observed materials in situ. You can make a climatology of the past 30 years or however long you have that measurement information. That is usually also a good explaining party, especially when you have that climatology in a seasonal picture, so that at least for every month you would have a separate climatology, or even for every day of the year. Those are good helping systems that, especially if you want to also downscale, help you to achieve that. Then we do use something like day of year and latitude and longitude many times for the fact that we can also understand the quality. So if latitude and longitudes, which generally shouldn't matter, are high up in the feature importance, that's still a kind of like indicator of maybe the model hasn't learned enough and we need more training data. Yeah, but one key is that when we use in the training ERA 5 and ERA 5 land material, what we want as when we do the inference prediction part of this, that we would have distributions that are similar to ERA 5 and ERA 5 land. Now, seasonal forecasts, for example, are distributed from the Copernicus Climate Change Service only at 1 degree resolution, which is very coarse. And in that seasonal forecast, there's also much less distribution, kind of spread of variables, even if it's an ensemble, than it actually has on, and the part of where it is also not correct necessarily. So it's really important that you do something called bias adjusting, and at the same time you can also do downscaling to this ERA 5 land resolution for the seasonal forecast. And that is by us done very straightforward with monthly statistics from 1995 to 2024 for all those variables that we want or need in the seasonal forecast output. So it's pretty much all the surface parameters. Then that is being just corrected by the, like when it's unbound variables with subtracting and adding. So a very simple, straightforward bias analysis. Some cases we also use the variance as an extra, but even just using simple bias with subtracting, adding kind of functions, because unbound variable treatment is giving a much more kind of like, it does not have the capacity to go very bad out of bounds. So if you have a divide and multiplying like bound variables you would have to need, so precipitation, for example, you might in a way a little bit explode that distribution sometimes. So to avoid that, if you can also a little bit juggle how those variables are being defined, that they are, for example, not bound at any point, but they are unbound and can be done with subtraction and adding. Yeah, but in any way, we have fixed bias. We usually do daily data sets and daily models. So this works. Obviously, when we do this on a monthly level, then there's a kind of like visible jump in the results that when a month's border is met, this is visible. We try to keep that in to remind people that this is not kind of like such an exact information, but you have to be aware of it. Yeah, but that's how we do that material. But now we can go to the Iceland case, which in that sense was a super kind of nice action that most of the time you actually spend in gathering the target data sets and then adding to it those predictors and features. But in this case, LamaH-Ice is a ready-made data set by Hörður Helgason and Bart Nijssen, since released in 2024, where really all those Iceland rivers that you can see on the map that have a kind of a stream flow measurement point at the end. All of those data sets have been put together, and there's very nicely watershed characteristics, so orographic features in the way of the catchment and other things that are important for this hydrological question. They are prepared already in this data set, so feature engineering is taken care of, but especially that the daily catchments hydrometeorological time series. So from Era 5 land, for example, you can see that these catchments are pretty big areas. They are not at all the same size. So they all each need to have a catchment-based average sum, or depending on the variable. And all of that is ready-made in this data set. So you don't have to do any pre-processing in a way for the data in this case. And then the target is directly there. So it's the daily observed stream flow, QOPS in the next slide. So, and we have that from 107 river basins. And the data set is actually pretty long. So since like over 20 years. Yeah, here just that you can see all the catchments. So some are also very small. Some are related to glaciers. So those white areas in the image, which is also actually from that research paper from Helgason and Nijssen. So also that glacier mass balance information is included per catchment where it's relevant or where it exists. Yeah. And of course the river network, like if there's a upstream kind of catchment, then all of that information is also included nicely in this one. And building that training data was in this case only combining from different files that this data set has the hierarchy of these that gauge network, so that you get the upstream downstream ID information also included in the predictors. And then we did some quality check so that in some cases some things were missing, that you don't include them in the training data set. And then you have a nice training data set. All those feature namings are almost like directly the columns that in the input data sets we had. And that made it very straightforward. Here's now an example of how to show those 107 rivers that were split into the training and validation in a way that 2013 to 2013 was the training data time, and then 2014 to 2018. So I was a little incorrect. We have 19 years of data, not 20, but that's very good. In any case, you can see that those rivers are very different, and that's good because we are trying to make one kind of forecast model for this stream flow. We are not making a separate model for each of these rivers. So it's actually nice that we have these huge rivers with like extremely large stream flows on some days, and then on other days they are actually relatively kind of quiet rivers, but then we have also these super small ones that even don't have any flow at some point in their yearly time frames. Yeah, maybe that's good for that. And then really just tuning with Optuna, the hyperparameters, and training the data. And then here you see now one of those SHAP bee swarm pictures from this modeling, and you can see that really important are the yesterday's and the day before yesterday lag terms. So how much was the river flow on the previous 2 days? Those are most important. Then you see that going from up down, that's really how big the area is. Very logical, I think. Things a little inverted. I can't remember what that was, but in essence, you can see that the precipitation obviously is pretty high up for the first one of these meteorological inputs, but a lot is actually defined by that existing history of flow, and then how that area is defined that has accumulates the flow. Very logical, very good, but what is almost incredibly good is when you look at the Pearson. So on the bottom of the slide, you can see the correlation coefficient being 0.988, or Klein-Gupta efficiency, which is something that, especially in hydrology, is being liked to be used for these kind of exercises, where the maximum is also 0.99. So we have a almost perfect modeling system in place for this, and mean absolute errors or root mean square error that you can also see here. They are very small when you consider that some of those river flows went into almost 3,000, 2,700. So compared to that, these errors of 1.7 or 7.3 are really small. So super good model. We wanted to also understand how that kind of relates to the different rivers. So calculating all those same, let's say, quality variables also for the performance matrix for each and every river. You can see that this Klein-Gupta on the right, being bold, is when it's over 95%. So a very large part of these is close to this perfect, and just a few, and here we highlighted more the correlation, that's 0.7 in some cases when it's not as good, and I think the worst cases were one river is really crazy, it goes to minus in these kind of performance matrices, but the other ones are even 41% or almost 50%, the ones that are not working so well, but 90% of everything is working close to perfect, and the rest is also acceptable, except this one river where there's something funny. But now we know we can super well predict and do a machine learning model for the Streamflow in Iceland. The only thing is that when you have these lag terms in, you actually do have a little bit more complicated production scheme, because you would have to always calculate just 1 day at a time forward and feed back in that lag from the 2 previous days. And well, we thought, what if generally it works so well, what if we try to not predict lag, but we would actually predict the delta? So how much does Streamflow change from 1 day to another as the target? Because then we would have a kind of production system where you can just calculate all days ahead directly without having to kind of feed back input from the previous day's forecast. Yeah, so we tried that. Similar production of the training data set. Obviously, you have to do the kind of calculating this delta and leaving out some of the columns that there are. And now we find a pretty different kind of model where you don't have so clear champion explainers. Maybe that's best on the that you can see that all kinds of variables have some meaning, but they are almost always just the weather-related ones. We have in these data sets a lot of those sums for days backwards, so in a way to try to give some of the history. Also, the weather terms were not just one day data always, but it is very unclear what is the most pressing, except precipitation, which seems to be also here in a good place. All the rest is a little bit fuzzy, and especially when you then look at the evaluation performance, you can see that this Q of delta, which you have now remembered that this is the one day to another change. So if the mean absolute error is actually worse when we had in the QOPS product, then you can understand that it's not very good, and especially when you now go to this NSE, so the Nash Sutcliffe efficiency, which is similar to Klingupta. Can't remember why Golda didn't get the Klingupta calculated, but in essence, when 1 is perfect, 0 is pretty much like not much, and if it goes negative, you're unsure what you even have. You can see that there's a very, very low kind of quality in that. And even when you, that's the training result. And then if you do just the training and validation, so the whole data set, so training result means that from the validation data set, those are the results. If you then take also the training time and validation time together, you a little bit improve these, but you're still almost kind of like just almost at the same result as this previous other model. So if you would then put this into a 215-day rollout where you calculate with kind of consecutive 215 days, and in this case not with real weather forecast problematics in there, so like forecast error is not in these, just those 215 days are being put in as kind of forecast, but there's no information from the previous day. So that will actually not change anything on this result. But when you then kind of like compare that now to this same recursive 215-day forecasting, where we are using the other model, you reach actually a Klingupta even at 215 days, that is 0.3, so very acceptable and useful still. Obviously, these mean absolute errors and RMSEs are then much higher, but when you compare those numbers also to the kind of 2,700 maximum that some of these rivers have, and these are pretty acceptable, all of them. So, very quick, simple conclusion. There's no point in doing a seasonal forecasting system with this delta forecasting. Here's also just not every river, but a bunch of these rivers that this 215-day forecast are there. You can see that here also the longer time frames sometimes make that more rivers not very useful is in 215 days ahead forecast, but that's pretty much to be expected. And going so what further into the future, this methodology will kind of add into this problem. Now, this 215-day forecast is used in a way that whatever it forecasted was put into the lags. So in a way, this was therefore a different result. So the lags were filled by what the model was predicting. But still, some rivers have even excellent Klingupta still. So if you are above 0.5, for example, very good Klingupta. Yeah, and the other metrics for this QOPS delta is everything is pretty much around 0. Yeah, so I think very simple conclusion. The universal streamflow model is kind of super feasible, but it requires the more complicated production where you actually have to use the lags. So you have to start with having 2 days of observations, and then you will have to kind of like by 1 day ahead going replace those lags with the forecasted information. And it is very simple to understand this, as in sense that Streamflow is such a kind of a problem, or the physics of this thing is so complicated in this large area where the water comes from, that you have to consider the history of past days in a way that is most simple to organize by having the lag of previous 2 days. So that's actually quite a nice thing, that the simple 2-day lags, you have enough long-term memory for this kind of a model. Yeah, but in this case, especially because Golda had to change and we have new people to work on it, we unfortunately couldn't for this presentation already have a 6-month Streamflow probabilities forecast for Iceland, which in a way we are working on. But even if the training was simple, analysis was simple, because we had this wonderful LamaH, you have to now consider that from that biosuggested seasonal forecast, we actually have to make all that more kind of time intensive production into scripts that can really extract for all those catchments that seasonal forecast information in a way that is aggregated. So some of them, some of the variables were sums of several days of an average, or a mean, or minimum and maximum in some cases. So you saw that, for example, the temperature was in very many different variables available in this LamaH system. So we have to kind of like map all of those together in the seasonal forecast material that we can really put in a production system. This work is on the way, and yeah, happy to share that information when it's done. But that's all I have. Thank you for your attention.
Thank you, Mikko, so much for your presentation. Now would be the time that we can take questions. So if you have questions, feel free to raise your hand and we will unmute you, or you can also put your question on chat. So for now, I do not see any raised hand. Maybe I go ahead with the first question, Mikko. You showed very nicely in some of your sharp value plots the role of 1 day before and 2 day before Streamflow in predicting what happens next. But a lot of these variables also had negative sensitivities or negative sharp values. Do you know what that means?
So in essence, what's on the kind of like the positive sharp value is always meaning that it adds to that kind of like it adds to that end result. So I think that you have to see those negative values are, or I think the temperature in this case, when it's a regression system where you get a number from, that positive is when it is lifting that number, and negative is when it's kind of like kind of depleting or making it lower that end result. So I think this is pretty simple for the understanding that does it raise or lower it. And in some cases, it's good to understand that lag obviously is the one when lag is high, then so it has a red number or a red dot. It is a high lag. Then it also means that it gives a high end result, because obviously it will not change so much from day 1 to day 2, for example, or to this day. That's how you can easily understand why the red dots are usually explaining it upwards. But like lag being low, so small lag numbers, it's kind of pretty obvious that that cannot give often more kind of like smaller lag, because it might be that there's no flow at all. So the no flows you can see here on the side, there's a stop to how the lags can act. But when it comes to that, and I can't now remember what the G area was. I'm too bad at this. Can't remember. There were so many of these different catchment, let's say, related kind of description terms. But that is just explaining, for example, that obviously when you have a very small catchment area, so I can't remember if G area was exactly that, but one of those areas is, of course, how small is that catchment in general. So a small catchment cannot give a very big value. So in this SHAP analysis, that's why those negative values or kind of blue values tend to shift that end result lower. So that's how you can relatively straightforward understand this. So red values mean that they are from that predictor a higher value, and then where on the SHAP, like left or right, it ends up, it explains, does it kind of raise the value or lower the value? And in many cases, it's I think in my experience so that it is usually so that some variables or some predictors kind of explain like higher values and some explain lower values. And you might see these also that sometimes the low values of a feature are actually raising them. So you need to see the swapping. Here, usually red dots are on the right side heightening and blue dots are lowering the value, but this is not so common when you have more the weather parameters, but I don't see on this slide. And well, total ET seems to be a little bit like that, but yeah, it's not like a lot of explanations here. Maybe on the when we look at the SHAPs from the other model where it was, yeah, here you have surface net thermal radiation mean, for example, is something where if there's low thermal radiation, then at the surface, then it actually kind of like can suggest more flow compared to lower one. But this is, yeah, and precipitation is super natural. If there's lots of precipitation, probably there will be more flow.
I think this makes sense also in this figure. We see that 2-meter temperature mean sum has a negative SHAP value but high importance. So I think it's clear that the color itself depicts the importance. Thanks for answering that. We have a question on chat from Ela. I'll read it out. Who manages these 107 catchments and what equipment data is installed there? And is the data transmitted in real time?
Yeah, so this, I think Landsvirkjun and the weather service in Iceland are together running, and I think Landsvirkjun, which is the kind of like national power company in Iceland, is probably running all the ones where hydro power plants are related to that flow. But I think we do have exceptionally many also natural flows in this. So if I go back to the map of these catchments, then when you see here in the middle, for example, many dots next to each other, that's actually the one river flow where there are several hydropower plants. So this is like a managed flow. But then if you go to, for example, the northern parts, I think there's like 2 power plants only. Lots of these rivers are actually totally natural, which is kind of like exceptional compared to in Europe. Almost no flows are natural. They are all managed by humans. But here, I think half of them are natural, and even the ones that are then managed, they are the smaller catchments with like even on the same river, several power plants. So I hope that answers the question.
And do you know if the data is also transmitted in real time?
Well, yes, we so at least for the daily. So now we got from Andre Gunnarsson. I don't know if he's on the call. He could answer even better. But we are having now we get every day the forecast, the observations from at least 30 of them, or was it even more? I can't exactly. I just saw the list yesterday in an email, so or on the website where we can download these data sets. So at least the ones where there is, so which Landsvirkjun is operating, so that's available for us to do for those particular rivers. They want this model to be run, so we have that data every day updated, so that we can run from any day that we would start this from the production. Then
Thanks for answering that. We also have a hand raise from Jonathan Coos, who is now on the panel.
I wanted to ask if you did a comparison, because now you modeled like all the flows in one huge model. Did you make any comparison if you like model just one separate flow and how it's performing, like this big general model compared to like this a single model for a single stream flow using the same or similar methodology?
Straightforward answer is no, because when the first model is already so good and we really had just one flow where it fails, all the others it worked. So, and in some maybe not super perfect, but still totally acceptable. So that's the reason. And then there's also the point behind this exercise is actually not just to use this model in Iceland. We will also try this model in the future in other places. Even there, we would try it in a way that what can an Iceland model actually perform well in Finland or in the Alps. That's one of the things that we will do, but haven't had time yet to that. So we did. So there, unfortunately, in this data set was not directly the kind of one field to say this is natural, this is unnatural. So you have to deduct this from kind of understanding those features that the catchment has, that some of that explains, then combined that this is a managed flow place. So that's why we have not done this particularly, but we know that generally, of course, this would make an even better model. But when we also want to make a production system, so the less things you have to handle, the better. So that's why the goal is really not to try to have a kind of complicated system with separate models for each of them. And I see Ekaterina kind of thinks that that's provocative, but maybe it's like that we don't separate natural and managed flows. The idea is that when you want to make a system where you could predict with a machine learning model any river in the world, then I think then you understand this exercise. So Iceland is the first stop, but we will, for example, go to the Himalayas to do some rivers there. We have alpine rivers, we have Finnish rivers, and they are managed, unmanaged, but to be able to do a forecast system on each of them, it's preferable, of course, to have one model to understand everything, because like the human part of this management is in some cases still something very predictable. So when the reservoir is very full, then they have to kind of like let it flow. When it's very low, then they can't let it flow a lot. So even the human management of this kind of rivers is not such that it doesn't actually kind of depend, especially on this lag term. So I think that lag term is therefore so powerful in this system, that with that you can actually explain also human management decisions.
Katrina also mentions that in case of lags that she would agree. She also had another question. I'm not sure if Katya wants to directly speak up or if I should
you can
just
raise
read
it also in voice.
Or Mariam, would it be possible to mute Ekaterina?
Yeah, okay. it's a bit noisy where I am, so that's why I chatted. But anyway, about legs, I would agree. In case, but you are like aiming for the seasonal forecast, that then you would need to get rid of those legs after all. And where like the difference between managed behavior and natural behavior would, from my perspective, pop out, and probably you I would try to separate those kind of watersheds and see how this seasonal forecast, how this factor of management, when you get rid of the lags, because like of course the lag is the best predictor in XGBoost model or anything like that. The next thing, probably I've missed it from your presentation. Did you try to feed your model with retrospective seasonal weather forecasts, or you only fed it with actual values from era land when you project for 15 days or something like that?
Yeah. So I tried to explain it. So we did not use a seasonal forecast, but we used like the feed in were like perfect weather forecasts for the next 215 days, but we did not use the lags that were available in that data set, but we made the lags from our forecast. So that's that kind of like comparison to doing a delta model, where equally we kind of fed it optimal weather forecast, in a way you could call that, because that's the ERA 5 data that we used. But as I said in the conclusions, we are building a system where we do have then real seasonal forecasts. And when that system is up, then we will also run like old cases so that we can like see how well did the seasonal forecast in a way work in Iceland, because that's of course one of the questions that determines it. But in this case, it was really and I would kind of like challenge you on the fact that it is good to do the natural and the kind of managed rivers separately. That when your goal is a universal model, and I totally believe so much in machine learning that it can learn both. There's no reason why an XG gradient boosting, especially when it's a decision tree thing, it can actually very simply kind of see, this is this case, this is the other case. This case I treat in the next steps like this, and this in another way. So I think it is actually very naturally kind of learning two different solutions in one model. So I don't see a reason why we should complicate ourselves on the production end by not just teaching with two. Like with all that material. So in that sense, and this is really the fact that we are going for a production system that we could then do. So the less complexion, the simpler we can do it. And as we do have to make all that aggregation for that material incoming. So 215 days of material has to be, for the catchments, always calculated into separate data that will be then fed into. That is actually a complication state already, and that's why we don't have it yet ready. so then there you might understand that why it's interesting to then not further complicate your system by having several different models. So that's the very logical reasoning, and I would really say that, especially when it comes to these kind of decision tree based systems like gradient boosting models, they can well work at the same time for natural, unnatural, or managed flows. It might be that it might become an overfitting problem maybe in other machine learning methods. So there it might be actually good to separate them up. But in this case, it shows to work, and we should have investigated a little bit better this one river that doesn't work. But I remember from Golda that when she looked at that river, it was also a river where much more data was missing. So this could be actually just more an explanation that whenever there was a bigger flow, the device measuring the flow didn't work. So we are missing like that spectrum of the options that could then get to a good model. So this could be simply the fact that that one observation is so faulty in its time series that it can't teach a model anyway. And that's how I feel, and all the rest was so good anyway that I don't see that it was so important to go after these differences, because we have really a goal in a one model should do it for even the rivers in Europe and in Himalayas.
Yeah, thank you. That's a good point, and probably that is really like that. But then even more, it would be interesting to see like this exercise, putting them and like to prove this point that like we throw them out and see like nothing changes, so we keep them. Like, probably,
and I think just
to silence those skeptics who would ask this kind of question.
And I totally think that's something that now Dilusha, I see, is joined in here. She will be the one to work on this further. That's one thing that we could do, that a managed flow kind of pool. What is the results for them compared to the natural? Like, how do they differ? That we can definitely do, but haven't done it yet, and changing people in this kind of a exercise is of course slowing us down for a while.
I was here for the whole session. I just saw that my name was your name.
You were the one with my name. Excellent. I was actually. So my wife is Annie Kröger. She's also on this kind of listening in. So I was wondering if she was just using my other laptop that is standing next to her where she's working. But okay. Yeah, but Dilusha is the person that could now, for example, check and kind of calculate that kind of performance matrices for the separation. But I can remember that it was not so simple as that there's one column that says this is a managed flow and this is natural flow. So we would also have to kind of like figure out with what kind of like characteristics of these catchments can we do that distinction. Obviously there is somewhere probably where are the hydropower plants. So there aren't that many in so Landsvirkning operating then, so you can go to landsvirkning.no to IS, and then they are actually probably they have something like 20 to 30. So from these 107, I would say that there's like 2/3 or even 3/4 are natural, and the rest is those managed ones. But we can go after that, and Dilusha is here now to have heard that request very clear, so we know what to do.
I was taking down notes. Okay, I have to address this and that. So I will look into that.
So thank you very much, Katarina. It's good suggestions, and we will pick them up.
Yeah, thanks a lot, Katja, for your inputs. Are there any more questions from participants? You can still raise your hands. We have a couple more minutes before we have to finish the webinar. In the meanwhile, maybe a question for you, Mikko, that you showed that this forecasting system works very well with XG boost kind of a model. Is this then also planned to be an operational system, or is this the first demonstration of what we could achieve in an operational setup?
Yeah, well, this is the model needs to be first developed to be then made, but we are running operationally soil water index. We are running operationally a precipitation forecasting, for example. So we do have some of these XG boost models in production, and they are not just in production for seasonal forecasts. We also do production from weather forecasts, which happens every day, and then once a month you get these seasonal forecasts. So in that sense, this is totally the plan for, and in CryoSCOPE, the idea is that we would have then a system now for Iceland. That we have still a few years to go with CryoSCOPE, that in these years they can every month see a new update to that forecast and kind of like see how useful it is actually in practice. So that's the goal. And yeah, that's why it will become operational.
Yeah. No, thanks a lot. Mikko, I don't see any more questions on chat or hands raised, so I would now take the opportunity to thank you again, and also looking forward to Delusha's work extending this already very interesting work. For the participants, our next webinar would be hosted on the 24th of June 2026, and we will send an invite about it soon. The next webinar would be on snow sublimation processes. And with that, I would like to thank Mikko for his presentation. Thank you all for attending today's presentation. And yeah, looking forward to seeing you next time. Also, thanks, Mariam, for organizing this.